Hello, class. So today we're going to start on section 4.7, which is called L'Hopital's rule. This is a very nice and very useful tool to know about computing limits. And in fact, it's something that I used a bunch of times in higher level classes, even in graduate level classes. So it's definitely something that's very good to know. It'll simplify a bunch of the limits that we were doing in previous sections, and then you'll see that it's very easy to use. It's a very easy technique to use. Okay, so there's this statement here. Instead of reading it, I'm just going to focus on this particular part. Okay, so the idea is if you want to calculate the limit as x approaches a of a quotient f of x over g of x, right, then that is actually equal to the limit as x approaches a of the quotient of the derivatives if, so the only one condition that you need is that both the limit of the top, so limit as x approaches a of f of x, and the limit as x approaches a of g of x equals 0. As long as that's true, then you can go from the limit of the ratio of the functions to the limit of the ratio of the derivatives. Now, the only other thing to be careful of is that if you see on the right-hand side of the equality, we have g prime of x in the denominator. So as long as that is not equal to 0, then we're good. Right? So that's this condition here, that you don't want g prime of x to be equal to 0. And that's basically it. That's the whole idea. Just let me note one thing here, and then we'll just jump right directly into an example. So the note I want to make is if you have something like this, so if the limit as x approaches a of f of x over g of x equals, well, not equals, but let me put it like this. You have that, and then you check that, and then you check this, the limit as x approaches a from the top, so f of x divided by the limit as x approaches a from the bottom. So remember, we can't do this if the limit of the bottom equals 0. Right? So that's why I don't write an equal sign there. I write an imply sign because we can't do this. But if doing this, on the top we get 0, and on the bottom we get 0, so we also write implies. So if the limit of the top and the limit of the bottom equals 0, so basically is the statement of the problem, then this form here, which I'm just going to write 0 over 0, this is called indeterminate. Indeterminate form. Okay. So if I ever write 0 over 0, I'm meaning that the limit of the top divided by the limit of the bottom, right? So the limit of the top is 0, the limit of the bottom is 0, right? So we call that an indeterminate form. So the idea is whenever we have a limit like this of a quotient and it's an indeterminate, then instead of looking at this limit, which you can't evaluate, right, because we're dividing by 0, you look at the limit of the derivatives instead. So it's crazy. To me, it's crazy to think that the limit of the ratio of the functions equals the limit of the ratio of the derivatives, because it seems like there's no relation. And in fact, it's really not very intuitive. There's a proof in the book. I won't go over it because it's very long. You can read over it. If you have questions, you can let me know. But it's definitely not intuitive. But it's crazy, and it's very nice that it works, because usually taking derivatives is going to make the work very simple. Now, the only other thing that I want to mention here is the second paragraph. The limit as x approaches a can be replaced by the limit as x approaches infinity or the limit as x approaches a from the right, right? It doesn't matter. As long as you're taking a limit, whether it's a limit as x approaches a from the right or left, or a limit as x approaches infinity, if you have 0 over 0, then it's an indeterminate. You can go to the derivatives instead. So that's the idea. Very simple, and let's go ahead and just try examples. So evaluate the following limits. Okay, so we start with a. We have the limit as x approaches -1 of x to the fourth plus x cubed plus 2x plus 2 divided by x plus 1. So notice here we can't plug in -1 because if we do that, we're dividing by 0 on the bottom. But if you note, if you take the limit of the top and the bottom, right? So if we check, so if I write instead the limit as x approaches -1 divided by the limit as x approaches -1 of the top, so this is x to the fourth plus x cubed plus 2x plus 2. On the bottom, we just have x plus 1. If we plug in. So here, both we can plug in the limit. It's a polynomial, right? So remember, it's plugging -1. What do we get? We get 0 over 0, right? So we get an indeterminate. What does that mean? We can use L'Hopital's rule. Okay, so what does L'Hopital's rule say? Instead of looking at the limit of the original quotient, look at the limit of the derivatives. So what does that say? So this equals, actually, let me just write it like this. It's probably easier. Let me write equals the limit as x approaches -1. Okay, so what's the derivative of the numerator? So that's 4x cubed plus 3x squared plus 2. What's the derivative of the bottom? 1. Okay, so you see, all I did is I took the derivative of the top and divided by the derivative of the bottom. That's what L'Hopital's rule says. Whenever you have an indeterminate 0 over 0, you can look at the quotient of the derivatives instead of the original functions. This we can evaluate directly because, well, the bottom is just a constant, so we're not going to be dividing by 0. Right? So it's just going to be, well, plugging -1, right? So -4 times -1 to the 3 plus 3 times -1 to the 2, or squared, plus 2, which is -4 plus 3. So -4 plus 3, that's -1, plus 2, that's 1. So see how simple. So this is a limit that what would we have done in class before? Well, we would have tried to factor the top, right? See if x plus 1 divides the top, and then factor that from the top and bottom and cancel it. Here, it's easier. Oh, it's indeterminate. Just take the derivative of the top and bottom and check the limit again. Right? So very simple. So that's part A. Let's do part B. I have the limit as x approaches 0 of e to the x minus 1 divided by x squared plus 3x. Right. So again, we can't evaluate the limit directly because if we plug in 0 to the bottom, we get 0. So instead, we check if L'Hopital's rule applies. We check if we have an indeterminate. So we check the limit as x approaches 0 of the top divided by the limit as x approaches 0 of the bottom. Right, so what do we get? So on the top, we can just plug in 0, right? You can evaluate the limit directly. E to the 0 is 1, minus 1 is 0. Right? So on the top, we get 0. On the bottom, well, we already saw we get 0, right? Again, we just evaluate directly, plugging 0 for x squared and x, and we get 0. So again, we get an indeterminate 0 over 0. We can use L'Hopital's rule. Right, so let's check here. So by L'Hopital's rule, and let me write the limit. So let me write it a little bit different, but the same thing I wrote before. If you do the x minus 1 over x squared plus 3x, by L'Hopital's rule, this equals the limit as x approaches 0 of the derivative of the top divided by the derivative of the bottom. What's the derivative of the top? Well, the derivative of e to the x is just e to the x. The derivative of 1 is 0. So we just get e to the x on the top divided by, what's the derivative of the bottom? Well, 2x plus 3. Now notice here, now we can evaluate directly because when we plug in 0 on the bottom, we don't get 0 anymore. So here we just evaluate directly, plug in 0 for x, e to the 0 is 1, 0 for x on the bottom, 2 times 0 is 0, plus 3 is 3. So see, very, very simple. And again, it's a very simple tool, not obvious why it works. Again, if you want to see why it works, you can go through the book and see the proof. For our purposes, really, it's just important to know you can always use this as long as you get an indeterminate form. But that's the only thing you have to check.